cool. Thanks everybody for coming to Chicago Clojure. First time we've had a speaker in a while, so I'd like to welcome Mitchell Skripinchik.
Oh, way wrong.
Sorry.
Skripinchik.
Cool. Sort of. I had like the right number of syllables. So I'm going to try to on that. Anyways.
You get an A for effort.
I got the chance to work with Mitchell briefly. He's a really smart guy. I was excited that he's going to do this talk about some stuff he's been working on with natural language parsing. I want to thank Phil for kind of wrangling him in and getting him here to do the talk. And if anybody needs Wi-Fi, it's right over there. Looks like everybody already found pizza. Otherwise, make yourself at home and enjoy the talk.
All right. On with the show. Just wait a moment. Hold on.
It's showing up here.
What are you seeing? You're seeing it? All right, excellent. Okay, good. Can we see my mouse too? Is that also showing up? It's showing up relative, so if it goes off screen. Okay, good. Yeah, that'll matter later on. But anyway, welcome everyone. My thanks to Joe and Phil for organizing this, and thanks everyone for coming. The topic of the talk is the Parse is right, using Clojure and Clojurescript to examine English. In the abstract of this talk, I had some unkind words to say regarding the reference of text as unstructured data. And I'd like to begin with talk to kind of re-emphasizing the point I made, namely, it is wrong to say that text is unstructured when there is a great deal of structure in text. And we do ourselves no favor to ignore the lessons that it can teach us. And just to drive that point home, here is that very sentence that you just saw drawn out of its structure in a constituent analysis of its syntax in English, using an app that I wrote with Clojure and Clojurescript. But we're getting a little ahead of the game. We'll be talking about that in a lot more detail. As far as the structure of this presentation, it will be divided into three broad parts. First, we will talk about the structure of natural language, which is broadly referred to as syntax, and I'll give a very quick overview of what it is and how it works. We will examine the syntax of the English language, and we'll be using a Clojure and Clojurescript app that I've written in the past year to do that. And we will also talk about some of the potential uses that this app has. It's more than just drawing pretty trees like what you just saw here. It has some actually very potent uses, as you will see in a bit. But syntax, what is syntax? Well, the American Heritage Dictionary, 4th edition, defines syntax as the study of the rules whereby words or other elements of sentence structure are combined to form grammatical sentences. Wiktionary, the dictionary arm of Wikipedia, defines syntax as a set of rules that govern how words are combined to form phrases and sentences. This is emblematic in the etymology, the word history of the word syntax, which derives from two ancient Greek terms, sun, which means together, and taxis, which means arrangements. You're literally saying arranging together when you say syntax. The original Greek syntaxis became the Latin syntactis, which then eventually became the English syntax. So that's the word that's actually used for the assembly of words into larger structures. A little bit more of elaboration on what that exactly means. Well, everyone knows that words can be classified as parts of speech. The canonical 8 parts of speech: noun, verb, adverb, adjective, and so on. Those parts of speech can be assembled into structures given the rules of English syntax. There's a to give a very quick example. In fact, the shortest example in the King James Version of the Bible, Jesus wept. It's the shortest verse in the English language King James Version of the Bible. 2 words from the book of John, chapter 11, verse 35. Well, everyone knows that Jesus is a noun and wept is a verb. English happens to have a rule that says that a noun and a verb can combine to form a sentence. In fact, there's the rule. It says noun plus verb equals sentence. And that's just one of a host of rules by which various words can lead to different various larger structures, and that those can then reassemble into other structures to basically form the panoply of sentence varieties that we see in English. What you're seeing here is a selection of what are referred to as gross surface combinatorics, a sampling of the ways that words can assemble into larger structures. And this is derived actually from a book of syntax that's called The Syntactic Phenomena of English, page 315, by Macaulay. No, not that Macaulay. This Macaulay. This is a photograph of James David Macaulay. He was a professor of linguistics at the University of Chicago and arguably one of the leading syntactic theorists of the 20th century. He passed away back in 1999. I found out about his passing on my birthday, it so happens. In his memory, since I've been working on an app that actually works in syntax, I've actually written this app in his memory, and I've named it after him. So the app is called Macaulay. So enough about syntax. This is a tech talk, so let's talk some tech. Let's talk about Macaulay the app. Well, there are two main components to this, at least as far as a graphical form goes. There is an API backend with a web endpoint that's written in Clojure and that uses the core natural language parser that is derived from the natural language processing group at Stanford University that's made available online, written in Java and compatible with Clojure. So that's what basically does the parsing. You give it this piece of text and it actually will draw a tree for you, and that takes the text as input and delivers back, as I've written it out, as a JSON object as an output. That JSON output is then fed into an HTML front end that you'll be seeing in a bit, which itself uses Clojure to write to JavaScript, and more particularly to the D3 graphics library in JavaScript that actually uses SVG, scalable vector graphics, to actually make a drawing and also have it animated. So it's Clojure to Clojure to JavaScript, and specifically to the D3 library in JavaScript. So that goes from text to drawing a tree. There is also a separate component that I've written that also talks to the API backend that takes a bunch of text or comments in a file. So you could have a bunch of text and that can actually be served as input, and it actually would then parse each line one by one and then deliver back the output with various bits of information and the tree of what it is you're inputting. So to see this in action, and to see some code, we'll take our canonical example, Jesus wept. So the text is up here. The web endpoint takes it as input kind of like this. This is the Macaulay API namespace that I've written that actually does the parsing, invoking some libraries from the NLP project at Stanford University, and also some affiliated Java utilities that we wind up using for data processing later on. That makes it a little bit easier. There is a, excuse me, a GitHub repo that Stanford has made available that actually interacts very nicely, and which I've actually utilized to some extent in the API forming of this app. This is the heart of the app. So basically take a text, you then put it through in a threading macro, taking a text as input, then you're running a tokenize function, which is right here. What that does is basically takes the text like Jesus wept and basically transforms it into a vector with a list of word objects, as they're called, so that Jesus would become a word object, wept would become a word object, and actually so would the period at the end of wept also become a word object. That's then tokenized. That is then input into a function parse that you basically see here. This is what does taking that vector of words and actually building a tree, doing two things. First, assigning parts of speech to each word where applicable, and also assembling those parts of speech into a syntactic tree. Most of the magic is actually done, if I can get my mouse to work, right here in the load parser. That's an alias to the the parser that you actually saw back here, the Lex parser. That is aliased as load parser here, and then delivers back out a structure that is then transformed into a string and then transformed again into a JSON object in this function transform CLJ obj. So to actually put this in more specific details, Jesus wept goes through the tokenizer, the parser, and then comes out like this. So you can actually see bits of the constituency that a tree would have. You would see that Jesus is a proper singular noun. That's what NNP means. These are, by the way, pen tags. It's a set of 36 different parts of speech that linguists at the University of Pennsylvania have assembled and that have made available, and that the Stanford processor that I use for the Macaulay app actually uses. So it winds up actually delivering parts of speech not by any kind of canonical sense, but by specifically using these pen tags from the University of Pennsylvania, as it's called. So Jesus is a proper singular noun, that's what NNP means. Wept is a past tense verb, that's what VBD means. And that's part of a constituent of a larger verb phrase, that's what VB means. And you can tell where constituents begin and end by the parentheses. So nesting beginning and ending refers to the beginning or ending of constituents. Same thing here with a noun phrase that subsumes the NNP, the singular proper noun, Jesus. And both the noun phrase and the verb phrase are in a more larger sense, assembled into an S, a sentence. So then that is then put into this hulking beast of code that basically then transforms that nested structure into a JSON object that more specifically is going to look like this. There are three main components that are set here for every word that you see in the structure. There is a part of speech. There is a word if it's applicable, and a lot of times it isn't. You actually see that here with the S, for example. It does not have a word affiliated with it, but a proper noun does have a word affiliated with it. And then children, if there are children available, this is what allows the nesting to take place to determine where various components fit within a structured hierarchy. So this structure, this JSON object, then becomes the input to a ClojureScript, JavaScript D3 front end that eventually digests that and produces a structure kind of like this. So it actually will draw this out using an SVG. So we'll be actually taking a look at the code to draw this out. But before I do, a little bit more about what you're seeing here. So even though this looks like a little bit of a gray canvas and a tree with lines and various blocks that represent things, there's a lot going on behind the scenes. For one, there is an SVG object, a scalable vector graphics object behind the scenes. That represents a JavaScript structure that itself has various components within it as a JavaScript list. For example, there is a list of links, as they're called. So there is in the D3 library that Macaulay uses, there is a tree drawing function, and that's what I wind up utilizing, and you'll see the code of that in a moment. And that tree drawing structure actually takes a JavaScript object and basically will automatically draw a tree for you if you give it a structure that follows the patterns that it's expecting. So it's expecting something with links, lines here, with nodes as they're called. So you're going to see various, would be dots under a normal tree, but here I've made as squares or sometimes as nested squares. And these nodes, like for example, wept here, itself also represents a structure. So you've got the part of speech, you've got the word, VBD in this example, you've got the word wept, you've got, and also the squares behind that in order to make it a little bit more readable. So this is a blue square and then a white square with the words themselves, VBD, the part of speech VBD, and the word wept as components in themselves. So you basically have four components: the part of speech, the word, and the respective boxes between the behind the part of speech and the word, all of which are also brought into bear for the drawing of this. So how does this all work in tandem? This is how. So we have an SVG drawing that makes an invocation to the D3 library, creating an SVG object specifying the height and width of the canvas we're going to be drawing on. This is the tree object I had mentioned, which actually this is the invocation in D3 to draw a tree and size it accordingly. That tree takes as input both a set of links and a set of nodes. And this is basically the way you invoke it, basically by taking, this is the tree that you pass it along, the Clojure CLJ tree, ClojureScript tree, that takes that as input, transforms it into JSON object, and invokes it using the JavaScript interop with ClojureScript into a nodes function to pass along then pass along again as a links function. So you're getting both the nodes, the various dots on the tree, and the links, the lines that connect them. The content of each of those respective nodes, in the example we had mentioned with wept, is handled, well, broadly speaking like this, that actually invokes the SVG structure of G for a graphic. So we're actually saying, I'm going to draw a graphic here, and I'm going to specify how that's going to be drawn in details. The data themselves are passed along here in this data invocation, and then you can then call that with various functions to follow for the specifics of how to draw it. And this is actually what we do. Well, actually, before I get to that, there are some helper functions that I actually invoke to actually make things a little bit easier. One for drawing the path of, so if you've got a line and you've got two dots that basically connect, well, a line connecting two dots. Path drawer is a function that basically takes the source and target, so imagining one dot and another dot, and then the specifications of that on an XY Cartesian plane, and then passing that along to deliver back the expectation for the D3 library to be able to invoke. That's what the M and the L refer to. That's basically how D3 knows, hey, I'm going to be drawing a dot, and it's going to appear somewhere in this XY axis, on this XY plane, and here are the coordinates where they live, and that's what and that's how you're able to tell the D3 library, this is where you're going to be drawing it. There's a part of speech color. This handles the, for example, the blue square in the example of wept. So there is a Clojure map that I've created called POS color, part of speech color, that takes each one of the parts of speech that you see or that are made available through the Pentags library, affiliates it to a part of speech, to a color, and then you're able to invoke it just by using a Clojure map. There is a specification here so that if it doesn't have a color, it just basically draws it into a shade of gray. That's what that happens to be. There's a function for getting the word length. It so happens this is useful because sometimes the part of speech and the word differ as far as their length goes. Sometimes the word is a lot longer than the part of speech that it's affiliated with. Sometimes it's the other way around. So this function get word length basically takes the characters in that word, maps them out to the varying word widths, and we have to do this because in the Helvetica font that I'm using here, there is, it's a non-monospace font. So we have to basically program in the widths of each of the characters in order to properly space out the width of the length and of the box that's drawn around it. So that's what word length does. Get node length basically handles the word length for the word and the word length for the part of speech, determining whatever is the largest using the max function and delivering out the result. Basically drawing out the whole box using the longer of either the width of the word or the part of speech in the node drawing. So as far as the actual details of the prospective nodes that we're drawing, well, we have an SVG call that we're able to then use. This is what is actually used for drawing each of the respective lines, a graphics function. We're using the graphics library in D3 called path that then transition allows you to animate, delaying by, in this case, I actually programmed it to 1/10 of a second. That's what the delay in MS is set to. And then an attribution using the path drawer function that we had seen before, drawing it to a gray line that's 2 pixels wide and that has no fill within those 2 pixels. The rectangle for the part of speech is handled here, so that for each of the respective links, we draw the rect, which is the D3 library function for a rectangle, specifying its location on the canvas that we're drawing, where we're basically getting the details of where it lives using the target function. In that JavaScript object I had mentioned, the x and y coordinates of where it lives on that plane, noting the height of the box, the fill, and transitioning a delay to basically animate it so it doesn't just appear all at once. It is actually delayed so it will appear in sequence by some delay in some structure there. Same process is more or less in play for the rectangle for the word. Again, we're drawing a rectangular object, specifying its XY location on a plane, filling it to be white, and then transitioning a little bit of a delay, and also specifying the width of the box if there is one. And that's what this if not function is basically using to specify that out. The word itself that's drawn in the case of wept, for example, in the Jesus wept example, specifying a text object, not a rectangle in this case. This is the D3 invocation for writing words. Transitioning in the program delay, the text if it appears, that's what it turns out that D3 has a text object that you're able to use for writing in text, not just drawing lines or boxes or anything else that D3 can draw, specifying its X, Y location on the parameter and filling it to be black behind a white background. And finally, the part of speech itself. So this is the VBD example in the wept example that we've seen. Again, one more time. Text example, transitioning in to make it animated, programming in at a delay, noting the text object that we actually pass it in to say that I'm going to be writing a word here, passing along the X and Y parameters here to note its location on a Cartesian grid, and filling in the white, filling in the text of the part of speech white behind a non-white background. In the case of the VBD wept example, that happened to be blue. So the result after all of this, which we will see in a moment, ta-da! So this is the app. This is Macaulay. So you basically type a sentence here. It will appear on the top. You will parse by pressing a parse and clear it by pressing a reset. If you can't think of a sentence, you can just type in a random button and it will then give you a random sentence and you can then parse it out. Thank you. If you need another sentence, no problem. There is also, I should mention, a battery of statistics that come out here. So just to mention some examples. Actually, let me get a better sentence that I can use. No, no, no. I want. Come on. There we go. That's a good one. What play is this from? All the world's a stage and all the men and women merely players? Ah, come on. No, it is Shakespeare though. And time's up. It's As You Like It. But the reason I mentioned this as a specific example, well, actually, I'll show you why, because it actually makes a distinction between words and parsed words. So to talk about some of the statistics that you see here, nodes refers to the respective boxes in this structure. There's a node, 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 there's a node. It counts 25 nodes that we're seeing here. Words basically refers to this thing broken up, chopping it by space, counting the result. That's words. Parsed words is different. So that, for example, here's a great example. All the world's a stage. This actually counts up here as a single word, but counts as two parsed words. All the world, and that's an abbreviation for is. All the world's a stage, and that's represented by a singular connecting verb. Copula is the technical term in linguistics, but it's represented by the equivalent of a form of to be. In this case, is. That's what VBZ means in this structure. So all the world is a stage. So that's actually, even though it represents a single word here, it represents two parsed words, world and z, or meaning short for world is in this case. So that actually counts as two parsed words, and we have a count of the number of parsed words in this structure. Propositions and number of propositions per 10 words refer to idea-bearing units. We will get to that in a lot more depth in a bit. And then the depth of the tree. So you actually are drawing a tree from top down. So this is actually counting up here 0, 1, 2, 3, 4 levels deep. Voila. Four levels deep. That's the max depth of this particular tree. And then a count of the most frequent nodes. There happen to be 3 determiners. That's what that means. That's the equivalent of the canonical form of an article, a, an, or the in English. So there's a determiner, there's a determiner, there's a determiner. S is sentence, now NP is noun phrase, NNS is it's plural non-proper noun, and then NN is singular non-proper noun. Yeah, so that's that. Would anyone like to submit a sentence to try this?
No, I would not like to submit a sentence.
Okay. No, I would not like to submit a sentence. Okay, Joe, here's what you got. Oh, this is interesting. So we've got an interjection. It's actually counting no as an interjection here. It's just a standard noun phrase, verb phrase. And there's also a little bit of color arithmetic here. So NP is red, VP's verbs are blue, and what's red and blue? Purple. I actually colored them all. All the verbs actually are shades of blue in this. Verb, verb phrase, modal verbs as well, like would. This is an adverb, not. to submit a sentence, and so on. Very cool. Back to the talk.
Numbers.
It handles it separately. There actually is a number class in Pentax to handle that. We can demonstrate that more in a bit, but anyway, back to the show. So we've seen it draw some trees, and that's kind of neat, but what are some more practical applications about this? I'll mention a couple of examples at play here. One is, well, this is actually something that you may have encountered with yourself whenever you're on social media. This is an excerpt from an exchange I saw with a friend of mine on Facebook, where he writes, Nathaniel is a friend of mine who lives in Seattle. He said, I mentioned not having ice cream on a comment on somebody else's post, and now all the internet ads are showing me ice cream, grumble. And of course, Ken then responds back sarcastically, that's terrible. You know what you should do? Try this delicious Banana Royale sundae from Baskin-Robbins. So the idea is that Facebook will just dumbly look for items that you happen to write that happen to correspond to their potential advertisers. In this example, ice cream. So, okay, that's great if you're just saying ice cream and that they're just blithely looking for ice cream and there's no additional context about that. Like, for example, you might not be in the mood to want to talk about ice cream, or there may be some negative connotations that might be related to you talking about ice cream. So application idea number one would be to use the trees that Macaulay generates, as well as an idea in syntax, which we'll talk about in a moment, called scope, to determine a smarter way of searching for words and their immediate surrounding context. Scope, in linguistics terms, and particularly in syntax, has a specific meaning. Again, our good friends, the American Heritage Dictionary, this time 5th edition, and Wiktionary, define scope as the range over a part of a sentence or discourse that a quantifier has an effect on, or the region of an utterance to which some modifying element applies. So to give a specific example, let's imagine that Nathaniel, our friend, had posted something like, I don't have any ice cream on Facebook. I don't have any ice cream draws out to a syntactic tree that looks like this. Now, we're going to be focusing on two, well, really three, but it's for purposes of analysis, two particular nodes. Ice cream and the nt, short for not, the negative particle that's an adverb in the sentence, I don't have any ice cream. It turns out that they are both within the same, the int happens to be within the, as it's called, scope of ice cream. You can actually draw a triangle that subsumes both nt and ice cream. And by virtue of that fact, you will know, at least in this example, that ice cream happens to be within the scope of something that has a negative connotation. So you would think that Facebook should be a little smarter and say, hey, wait a minute, this person wrote about ice cream, but they didn't seem to write about it with some kind of positive connotation. Maybe I shouldn't post an ad. So now you can use a tool like this because you now have the trees where you can do some kind of analysis like this. And this could be an application that could more, for example, precisely refine the advertisers and social media networks. But aside from helping to fill Mark Zuckerberg's coffers even more so, there's an additional use for this that I'll mention with an example having to do with neurodegenerative diseases. You can actually use the data generated by Macaulay to help diagnose the risk and likelihood of things like Alzheimer's. And this is where the NUN study comes into play. There's been an ongoing research project that's now based in the University of Minnesota, where a population of about 670 nuns affiliated with the School Sisters of Notre Dame have joined in a project to basically use themselves as basically ongoing large-scale living guinea pigs to examine neurodegenerative disease research. Nuns, in particular the School Sisters of Notre Dame, are, as far as social science research goes, is concerned, a gold mine. It's a relatively homogeneous population. They're all the same sex. They're all relatively homogeneous in terms of things like they haven't taken any drugs, they don't drink, they don't smoke, they're presumably all celibate. They're all, as far as social science research goes, relatively consistent. And so this means it's a lot easier to be able to tease out things like, for example, confounding variables like your educational background or what you did in the course of your 20s or 30s. In one particular research issue, they basically looked at autobiographies. It turns out that when nuns for the school sisters join the convent, they are required to write a brief autobiography about themselves. And they actually got a cache of autobiographies of nuns from 1930 in a pair of convents in Baltimore and in Milwaukee. And they had a reasonable size amount of them. And the nice thing about this is that not only did they have these biographies, they also had basically the entire subsequent life history of all of these nuns going through the subsequent, now, almost 8 decades. So what they wound up doing was to basically correlate their future life history with what they wrote in those autobiographies in their 20s back in 1930, because we have that research. The result of that, as published in the Annals of the New York Academy of Sciences, ANYAS, one study actually researched saying that low idea density had strong and consistent associations with the risk of dementia and premature death. What is idea density and how does it relate to the syntax that we've been talking about here? Here's how. The article goes on to describe what idea density is. Idea density was defined as the average number of ideas expressed per 10 words for the last 10 sentences of each autobiography. Ideas, here in the specific technical sense in psychology and neuro-linguistic research, correspond to elementary propositions. They typically correspond to a verb, adjective, adverb, or prepositional phrase. And it turns out that Macaulay is perfect for this sorts of analysis. In fact, I've actually restylized Macaulay to actually deliver the output of that here. I actually have taken one of the sample sentences that they actually quote in the paper, put it through Macaulay, changed the coloring of the output so that you only see those ideas as this kind of yellowish-orange color, and everything else grayed out. And it turns out that you have, as the paper actually quotes, 7 ideas. So you actually can count them here, there are 7, and you actually have, as the technical literature terms, propositions. That's the technical term for these ideas, or idea-bearing units, the verb, adverb, adjective, prepositional phrase. And it turns out that they have a count, and also a more effective count as far as the research goes, the number of those propositions for every 10 words. And it turns out I've written the calculation of that to be delivered out here, rounded down. How does that work as far as Clojure is concerned? This is how. We have a function called compute tree stats. Taking a tree, you're then getting the sequence of that where you're basically taking in a node type, in this example, the POS, part of speech. This is now the JSON object that we're seeing. So you're basically filtering out those parts of speech, running through a threading macro, a tree sequence to basically get those lists of parts of speech that you're delivering back out, filtering out only those that happen to correspond to the particular node and that happen to be maps, and then getting those maps that are back out. That then is set to a temporary, can then be applied to this part of speech. The output of that put through yet another threading macro can then be filtered by the parts of speech that correspond to idea-bearing units, the propositions as they're called, filtering them out and simply getting a count. And that corresponds to the number of propositions. Number of words, simple split using the Clojure string macro, using the space as a regular expression. Start text happens to be the atom within the the ClojureScript side. For the text that you're actually typing in. So you're taking the text you type in, splitting on a space, and counting the result. That's your number of words. And then idea density simply is taking those number of propositions that you compute, dividing by the number of words per 10 units, so that basically means you have to multiply it by 10, and then transforming that into an integer. And that's what you get back. The code is online. There are 3 repos, one for the API, another for the HTML, the API backend, the HTML front end, and the bulk processor that we have. My thanks to colleagues at my job at Opinion Lab who've helped with the development of this and for back and forth on this, in particular highlighting the first 2 names on this list, Sebastian Alnode, who had helped a lot in the development of this going back to when it was just a simple, where I was trying to just draw a single dot in JavaScript, and our own John Jacobson, who's right here, who helped with a lot of the development and more recent refining the code in this pull request. So thank you both Sebastian and John. Any questions? Thank you very much. Any questions, thoughts, brainstorms? Yes, sir.
Where do the random sentences come from?
I'm sorry, say again, please.
Are the random sentences just hard coded? coded or?
The random sentences are hard-coded. Yes, I actually have a random sentence function where I just wrote in 30 functions. I had the idea of using a read string function to actually read from a separate file, so I could just populate the file. The problem with that was that that doesn't play nice with ClojureScript, as I found. I just simply hard-coded in a list of like 30 random sentences, and then from like all endeavors of life and the universe and everything. Yes, sir.
So I saw in the All the World's a Stage example that there were 3 units that were sentences, where the parent node was an S, and some of them looked like I think it was one was a conjunction, and one was I think an independent clause, and one was a
Yeah, go on, I'm listening.
I wouldn't have recognized each of those as being a full sentence. So how is it that those are? Is it because they correspond to one of those trees that you showed at the beginning that are definitionally a full sentence?
Let's reparse that and I will answer that. So
Well, I think and was a
all the world's a stage and all the men. I think we're missing a comma here.
I think and was a start new sentence.
Yeah, it was 2 sentences.
Okay.
Oh,
All the world a stage, comma, parse. Yeah, this is not matching up exactly with what I did. I think I'm typing it in wrong. Sometimes Macaulay can be a little peculiar, but sorry.
Maybe and was capitalized.
Yeah, that you might be right there. Okay, so let's try that. So we reset, type, parse. There we go. Okay.
Yeah. Okay. So is that driven by capitalization, or why is that?
It's driven by a lot of things. There is capitalization comes into play, punctuation comes into play, the periods, commas. Unfortunately or fortunately, the various elements that have little to do with the words themselves, but basically related to punctuation, spacing, capitalization, also apparently have an impact on the parser and on the output. So as you've seen, actually with this example, where I could change, so you see one tree, taking the very same sentence and just transforming that a and to a lowercase and, reset, repaste, parse, and now it's different, see? It's less flat and is actually delivering out a 5 depth, 0, 1, 2, 3, 4, 5. So that's only because in this example it so happens that and happens to be lowercase.
Okay.
So that's just an idiosyncrasy of how the parsing engine works. Other questions?
Hey,
Yeah,
this
Phil.
is just a random observation. There's Shakespeare has fewer propositions per 10 words than the nouns.
Yes. Yes, Shakespeare is not as verbose.
And I'm just kind of curious, what was like the number that indicated dementia?
The number, that's a great question. What's the number that indicated dementia? When you actually look at the research, the number happens to be, well, the number where you're basically in a safe zone is roughly 4 to 5 per 10 words.
Oh, wow.
Yeah, so it's like if you're in the threat, and that's the thing here, it's like you're trying to conflate things and you're only dealing with 10 words. It turns out the safe zone is roughly like 4 to 5. Less than that, roughly 2 to 3 is really precarious, as it's found. Yeah. So lard your speech with lots of verbs, adverbs, adjectives, and prepositional phrases, folks. That's a tip. Yeah.
Also, why did you choose to do the defining words as spaces instead of using what you've calculated elsewhere, presumably through the library's parsed words?
I'd like to, the reason I did that was because I wanted to have different ways of basically chopping up the same set. So you've got, it already provides the parsed words that's defined, and then a conventional use, and that is actually, in my experience, is not a bad way to actually represent words, just by dividing it by spaces. So it actually not only is pretty useful in what most people think of, but it turns out to be pretty accurate. So ultimately that's why, having basically 2 ways of chopping up the same thing.
Well, why does the propositions per 10 words use the space instead of the parsed words?
That's only an idiosyncrasy of me adding in that value there. So I'm basically saying, take that value, putting it into the into what's calculated here, and it's just an arbitrary choice on my part. No reason you couldn't just swap out another value for the number of parsed words instead. Yeah, I also wanted it to match what the literature that I had read matched. So that's an answer. Yeah, but I mean, they're all variables. You can mix and match them however you like. Other questions? Yes, sir.
What are you going to do next with it?
I'm sorry, say again?
What are you going to do next
What am I going to do next with this? Well, I'm talking to some venture capitalists next week, and then actually, I'm not sure what I'm going to do with this. I would like to. I've actually reserved the parsesright.com as a domain. I'm actually thinking of maybe starting a blog where I could do like analysis of like the stupid things that Donald Trump said and putting them through Macaulay and being able to taking like every speech he's given in the last year and seeing that and then because now we've got bulk analyses of all of this available. So run it through Macaulay and I've got a bulk parser for doing that. That's crossed my mind. I've reserved the domain maybe in like the next month or two if time permits. I'll do that. I would like to try to do something related to this as a useful tool related to providing something where you can actually examine your own words for like your own rough diagnosis of your likelihood of coming down with Alzheimer's. Not to say that it's like one, if you score badly on it, you're going to get Alzheimer's in your 70s or anything like that. No, but it would be one tool, and it actually could be pretty useful. You actually see, I've seen a couple of papers in the literature that are trying to, and they're like kind of like 15 years old by now, trying to calculate quick and dirty ways to get at those numbers. But now we don't have to do quick and dirty ways. You can just put the text in or put it into a text file, run the bulk processor on it, get those numbers back. So why not make that an app or some kind of tool that might be, you could download it onto your cell phone, or that could take, like for example, every email you've ever written. Take 15 years worth of that. Gmail's been around 11 years. So you could harvest every email you've ever written, put that through Macaulay, calculate out your number of propositions per 10 words, and see that. No, I mean, that could be a useful metric. I mean, it proved out to me, the original research about this was a lead story in the Journal of the American Medical Association back in 1996 when it was first published. There's been subsequent research in the 5 years thereafter. But no, I mean, that could be another useful thing. Yeah. Yes, sir?
What steps would be involved in sort of scaling this to other languages?
What steps would be involved for scaling this to other languages? A couple of things. One is you would have to have a language that actually lends itself to this kind of constituent analysis, and not all languages do. You have, for example, languages that are linguists refer to as agglutinative. So instead of actually taking distinct words that basically can be assembled into larger abstractions, kind of like this, they actually, like a single utterance, the equivalent of a word would actually be the equivalent of a sentence. You can actually say a full thing, but you wouldn't see that kind of neat breakage. So one thing is you'd have to have a language that does that. For most of the world's languages and the most populous of those, they do. Theoretically, all you need to do is basically swap out the parser for different languages. It so happens that Stanford University's Core NLP project has parsers in, let's see, French, Arabic, Mandarin Chinese, Bulgarian, Portuguese. They may have a Spanish one, but I'm not sure. So there's no reason if a language does that, then yeah, you could say write an Arabic parser. Voila, suddenly all the Arabic speakers in the world have a parser. You can see the trees there. You may be able to glean some information that's useful about that. I mean, it's the same thing for Mandarin Chinese. Most widely spoken, well, as far as the number of speakers goes, the most popular language in the world. And suddenly you've got that, and you can draw trees, and you can see structures, and you can discern or find out interesting things, or use them in interesting ways, like with this Facebook example I contrived. So there's no reason otherwise. The framing is there. Theoretically, it should be a matter of just swapping out one language for another, if you have them. No? Yes? Anyone? Yeah?
How feasible would it be to connect the front end to like a standard programming language parser?
What do you mean by front? Can you give me an example? I don't think I understand.
Like if I give a bunch of Ruby code,
okay.
Visually kind of see the structure of a specific program or...
Yeah, that could be hard. Yeah, that's a good question. You'd have to have a parser that would be able to recognize, let's say, Ruby, Clojure, whatever language. So the trick is with the parser. But theoretically, it should be the same thing. I mean, you're just swapping out, in this case, other human languages, but there's no reason you couldn't also do that for a programming language. I mean, that's what a parser literally is. So yeah, if you've got a parser where you give in Clojure code, let's say, Yeah, and then it would be able to parse that out. It would draw trees and be able to draw a structure like that. If you've got the parser that can recognize that text and understand its rules, yeah, it should work just fine, assuming it plugs and play okay. John?
Having played with this parse a bit and having looked at this code, it wouldn't be drop-in, but it wouldn't be that much work to adapt.
Okay.
This might be interesting to like take Ruby's actual parser or any
Yeah.
language parser and kind of run stuff through it and say, whoa, you might be able to tease out some inconsistencies.
Yeah.
Like rule something out as this solution is too complex. To be able to convey that visually to the programmer, that might be kind of interesting too.
That's how like, a lot of IDE tools work.
Should check.
Ruby is one of the harder languages to do that to. But,
I have a list of, no, it's not here. What I'm doing is I'm going to see if I have like a bunch of test sentences. No, I think it's in the HTML.
yeah, you want like
Other questions?
I guess Pro 60 would.
Ah. Okay, let's pick some really long sentences. Here's a nice one. The outbreak, there we go. I'm gonna copy that. So reset and paste. The full sentence is, the outbreak of the liberal revolution in 1820 in Lisbon compelled Pedro I's father to return to Portugal in April 1821, leaving him to rule Brazil as regent. Ta-da!
You didn't have to say a screenshot from the Siddhartha, did you?
I did not, no. Well, maybe I did. I actually put that in HipChat. What John is referring to is there is a sentence in the novel Siddhartha by Hermann Hesse that happened to be the deepest tree in that novel, 36 levels deep. This happens to be a meager 10 levels deep. I sent it into the water cooler in HipChat. Should I bring it up?
Yeah, like 4 times.
Yeah, so imagine this, it's really hard to read because it's that's the thing here, and that's one peculiarity I've noticed about this. The D3 tree structure that's drawn here basically just imagines the nodes as being dots. It doesn't make, like for example here, like revolution happens to be overlapping the word liberal. As far as, these are actually spaced correctly, assuming these are dots. But they're not dots. They actually carry node values. And so you have this little bit of an overlap here. There's actually spacing here. Most of the time this works, but that might be an additional improvement to this so that the D3 recognizes, hey, these are nodes here that need a little bit of spacing and they actually have a size to them. So space them out a little bit better. So that's one thing I haven't yet done, but by and large, for the most part, 4 sentences that basically fit within this box, it seems to work okay. Yeah, another question?
First off, I think it'd be pretty fun to see what that tree would, or just any tree would flatten out to if you just did like a DFS and then reassemble it.
Okay.
But then the other thing I was curious about is like, why did you choose to use Clojure for this?
Why did I use Clojure for this? A couple reasons. One is that the delving of this had an assortment of various tasks that I felt Clojure was basically suitable for. It was also a little bit of an excuse for me to learn not only the D3 library, but also Clojure And it was just fun to program it. I mean, it's just like, it had everything as far as the full stack from the back end, and also the library was itself most conveniently written in Java, so it played nicely with Clojure. And I could take it all the way through to D3, and also a way for me to be able to learn a little ClojureScript, which I wanted to learn, didn't know. Now I know a lot more about it. But yeah, so yeah, that's why. Other question?
Correctness of grammar or like quality and quality.
Oh, you're getting judgment calls now?
I know other people do, so
Yeah.
I want a machine to tell me that I'm smart.
That is and that's an interesting question. There's an app called Grammarly that actually not only does that, but also makes judgment calls regarding your speech. And they've put in thousands of rules regarding, for example, making sure that when your verb should match the plurality of your noun. So that it's Jesus wept, not Jesus, Jesus weeps, not Jesus weep, for example. So it'll note, peculiarities like that. But that's basically I imagine there's probably some tree parsing behind the scenes there. That would require a lot more than just this parsing because you'd have to add in and program in judgment calls, like for example, singular plural verb agreement, and saying, okay, this if you're not doing this, red flag, error, say something bad. So there's no reason you couldn't program that in, and there are apps out there that do that. I mean, that is also the distinction that linguists make between descriptivism, just showing how it works, and prescriptivism, giving some kind of judgment call and saying how you think it should work or be. Linguists tend to basically fall along the lines of the kind of scientific, I just determine how this works. I don't merely make a judgment call about whether or not I think it's good or bad. The other ones who fall under a realm of what's called prescriptivism do that. There may be some reasons for that. They may be good or not, or there may be some biases that might be construed related to any of a number of societal biases that might be construed with that, in which when you actually do the research, usually is. As far as the actual merit about that, it's usually along the lines of, I don't like you and I'm trying to discriminate against you and I might as well just make fun of how you talk. That sort of thing. Yes, sir?
The Shakespeare example is ungrammatical because it has a comma and a conjunction and an independent clause for the second half.
Uh-huh.
that made an OP mess up and mislabel in the second half. That's interesting.
That's true, and actually sometimes if it doesn't parse, it turns out that Macaulay will actually reclassify it not as a sentence, but as a sentence fragment. It actually comes as a tag called frag, F-R-A-G. So if it doesn't parse, and then you can actually give it, in fact, here's an example. There's a book by the author Italo Calvino. If on a lonely night, a traveler. Now that's the whole title. That is ungrammatical and actually comes back as a fragment. Because it's not a sentence. Because you've got a prepositional phrase followed by a noun phrase, no verb, that doesn't follow the rules to actually create a sentence. That's not a sentence, that is by default a fragment. So yeah, it can do that too. And that actually may be something else to note there regarding the text that you analyze. Maybe calculate the percentage of words or sentences that are actually not sentences but instead fragments. That could be a useful metric too. Have I answered every question?
Everything you say from now on, you're going to type in.
Absolutely. Everything I say goes in Macaulay and is being drawn down. And that goes for all of you, by the way. every text, every email, every tweet, all of it. And that's the thing here about this. When people, I'll leave it at this as far as my own personal rants. I kind of began with a rant, I'm going to end with a rant. People usually tend to think of language basically in the level of words. That it's just a soup of words. To some extent that's true, they're words, but they're not in a soup. They're in a structure, in trees. In fact, practically every time you talk or type or give some utterance of some kind, you're not just spilling out words, you are assembling trees, sometimes exceedingly complicated trees. There's a lot that can be learned out of that. And I built a tool that can start a little bit of that digging. Thank you.
So are you recorded that? Are you going to put that up?
I want to. I hope I recorded it. New screen.
Okay.
Hold on. I want to. Yes, I want to save. This is saved as DevMynd. TPIR 20.
I have a USB key.
Okay. Hold on. Yeah. Yes. We can do that right now. Stand by. I need to save this.
Yeah.
Save.